questions from the review that I've given you. First one is, in a police rifle test, a 15-gram bullet traveling 213 meters per second in a vertical direction suddenly buries itself in a 2.4 kilogram block of wood at rest directly above it. As a result, the bullet and block combination moves vertically upward. Find the velocity of the bullet block combination. Find the maximum height, and is the kinetic energy conserved? So this is a clear case of conservation of momentum, because the total initial momentum should be equal to the total final momentum. Understand that the bullet is fired vertically into a block and it gets stuck in the block and they move together. So applying the law of conservation of momentum, we can calculate all these quantities, especially the first quantity. Here are the given quantities. The mass of the bullet is 0.015 kilogram. Velocity of the bullet 213 meters per second. The mass of the wood is 2.4 kilogram. So the total momentum before is equal to the total momentum after. And this is 0 because the block of wood is not initially moving. And you add the masses because they get combined together and they move with this velocity which we are trying to find. On substitution and calculation, we get the velocity as 1.32 meters per second. Now, you have to find the maximum height. We have the initial velocity, which is 1.32 meters per second. Final velocity is going to be 0 at the maximum height. Acceleration is negative 9.8 meters per second squared, and we're looking for the vertical height. So we can use this formula. Vf squared is V naught squared plus 2a delta y, and substitute the values given. We get delta y as 0.089 meter. And the third part is kinetic energy conserved in this collision? No, kinetic energy is not conserved in this collision because this is a perfectly inelastic collision, because the two objects combine together after collision and maximum kinetic energy is lost. I just wanted to show the initial and the final kinetic energies so that you notice the huge difference. Now, here is the initial kinetic energy of the bullet. So plug in the mass of the bullet and the initial velocity, you get 340.3 joules. And the final kinetic energy is 1/2 the total mass times that velocity squared, which gives only 2.1 joules. So a lot of kinetic energy is lost. Look at the difference in the numbers. In this question, a small 1.4 Newton stone slides down a frictionless bowl starting from rest at the rim. The bowl itself is a hemisphere of radius 75 centimeters. Just as the stone reaches the bottom of the bowl, how hard is the bowl pushing on it? Now, here is the setup. So that's the bowl, and the stone slides down from here, from rest, and then reaches at this point. And we're asked to find how hard the ball is pushing back on it, which means we have to find the normal reaction. So when you look at the forces acting at this point, you have the weight acting vertically down, and you have the normal force acting in the opposite direction, and the net force must be the centripetal force. So that's the idea. So that's the normal force, that's the weight, and the net force is N minus mg because they are in opposite directions, and this must be equal to the centripetal force, which is mv squared by r. So now it's easy to find the normal force, which is what we are asked to calculate. And the mass we have to find, because what is given is the weight, which is mg. So from mg we can calculate the mass. It is 0.143 kilogram. And then we have to find the velocity by using mgh is equal to 1/2 times mass times velocity squared, which gives 2g times the height, and then plug that back in. So it's 2 times g times 0.75, which gives 3.83 meter per second, and then plug it back in here, mass times velocity squared by radius plus mg. Mg is 1.4. So when you do that, you get 4.2 newtons. Here is the next question. A 3 kilogram brick rests on a perfectly smooth ramp inclined at 34 degrees above the horizontal. The brick is kept from sliding down the plane by an ideal spring that is aligned with the surface and attached to a wall above the brick. The spring has a spring constant of 120 Newton per meter. By how much does the spring stretch with the brick attached? Now, to find how much the spring stretches, we have to find the force acting on the spring and then apply it in the spring formula. So that's the ramp. Here is the spring and the brick. The forces acting on the brick are its weight mg vertically down, but that can be broken up into horizontal and vertical. In this case, we only need mg sine theta, which is the horizontal, where theta is the angle given. So now we know that the force trying to stretch the spring is mg sine theta. So let's calculate that. Mass times g times sine 34 gives us 16.44 newtons, and then apply this in the spring formula, which is F is equal to K delta X. K is called the spring constant, and that is given. So we can find how much the spring stretches. We get 0.137 meter. The last question here is, you push downward on a trunk at an angle 25 degrees below the horizontal with a force of 750 Newton. If the trunk is on a flat surface and the coefficient of static friction between the surface and the trunk is 0.61, what is the most massive trunk you will be able to move? So we are asked to find the mass of the trunk, the greatest mass that we could move. So we need a diagram for this. You're pushing down on the trunk. That's how you're pushing. That's how you're applying the force. And the angle is 34 degrees below the horizontal. So actually the angle given is this angle here, which will be the same as this. Oh, that's, what's the angle? Is it 25 degrees? Okay. So now we need to break that force into its components. Here we have the horizontal and the vertical. The horizontal is going to be 750 cosine 25, and the vertical is 750 sine 25. There are other forces that act. We will come to that later. The weight on this is acting vertically down, and there is friction. Okay, here it is. We have the weight mg acting vertically down. We have the normal force up, and then we have friction against the motion. So when we look at the forces along the y-axis, you have n up, and then the other two are down. That's why I've taken them as negative. So n minus 317 minus mg is equal to 0, which gives n is equal to 317 plus mg. And knowing n, we can now plug it back into this equation and get the value of friction. So that's what I've done there, and I've distributed this to get 193, and 0.61 times 9.8 is 5.98. Now looking at the forces on the x-axis, there are only two forces. One is the 680 Newton we are applying, the other is the force of friction. So the 680 Newton should be just equal to friction so that it moves, right? And I've set it as equal to mass times acceleration equal to 0 because acceleration is 0. So 680 is equal to the friction, but we got friction as this expression, so I'm going to substitute that and solve. You get mass is equal to 81.4 kilogram.